kinetic energy. Okay, so kinetic energy is, definitionally speaking, energy of motion. And if something is moving, it has the ability to do work on something else. As I just showed you, the moving car can do work on something else. If it bumps into it, it can now apply a force over a distance. So let's go ahead and derive the equation for this. So we're going to just use the concept of conservation of energy, which says E initial equals E final. Okay, so our initial energy in the example I gave you was work. Well, what's the equation for work? Well, in this case it will be E final, but what's the equation for work? Force parallel to distance, right? So we'll go FD. So I'm going to derive this using other equations that you've seen before. For example, what's the equation for force? I'll do it on the side. F equals what? MA. More generically, MA. It could be MG in certain cases, but MA, right? So let's go ahead and substitute in F over here. So we're going to get work is equal to MAD. Okay, AD. Now this is also D. This is distance. This is also displacement as well. Technically it should be displacement, but we've made the distance to displacement in all the problems we've used. I'm going to group A and D together and use another familiar equation. We're going to use the kinematics equation. It looks like this. Vf squared equals Vi squared plus 2AD, or delta D. Alright, let's rearrange this so that we have our AD together. So this would be like Vf squared minus Vi squared. I'm going to write it like this. 1/2 Vf squared minus 1/2 Vi squared equals AD. And then we'll just make this substitution, the AD for the AD. So what we're left with is, we're just going to multiply this by m, right? So we're left with 1/2 mv final squared minus 1/2 mv initial squared. Now this expression right here, 1/2 mv squared, is what we call kinetic energy. So this is the equation, this is the expression for kinetic energy, okay, energy of motion. So let's write that here. This kinetic energy equals 1/2 mv squared. Notice that kinetic energy is dependent on two things. What are the two things? Mass and velocity. Hopefully this makes sense, right? If I show you this example again, if I have my car going slowly, can't do much work, right? If I have my car going quickly, it can do a lot more work on something, okay? So velocity is a factor. Also the mass. If I take this small mass object and I roll it into FUFAR, not a lot of work. If I take a big mass object, more work, right? So mass and velocity are both factors. What's the stronger factor, mass, velocity, or are they equal, 50-50 partners? Velocity is, yeah, how come? Because of the squared factor, right? So for example, if I double the mass, what happens to the kinetic energy? It doubles. If I double the velocity, what happens to the kinetic energy? Quadruples, right? 2 squared times stronger. This is why they say, like, when you're driving, if you go faster, it doesn't just have a little bit more energy, it's a lot of more energy, right? If you double your speed, you can't do twice as much damage to something else. You can do 4 times as much, okay? All right, so let's just keep going with this. So I could write this then as KE, what's the difference between these two? Yeah, they're the same except one is a final and one's initial. So we could write this as KE final minus KE initial. Well, what is a difference here? What is this when you subtract final minus initial? They're not going to be equal to each other. This is called a change, or a delta. You're changing from one to the next. You're finding the difference between the two. So I can write this as delta KE. Okay, now I don't expect you to necessarily memorize this derivation. I just want to show you that it's coming from somewhere, coming through from familiar concepts, F equals ma, kinematics, conservation of energy. Okay, but the two things you should know are the equation for kinetic, the expression for it, and this concept, work equals delta kinetic energy. Now this is not a hard concept, okay? If this has 0 joules, it's not moving, right? If I do 10 joules of work, how much energy does it now have? 10 joules. So the change in kinetic, it started out at 0, I did 10 joules of work, it now has 10 joules of kinetic. What if it was moving? What if this was moving slowly? Let's say it has 10 joules, and then I give it another 20 joules. How much energy does it have at the end? 30 joules, right? It started with 10, I gave it 20 joules of work, it now has 30. So the change went from 10 to 30, 20 joules was the change. Work equals the change. Okay?